صباح الخير للجميع. أهلا بكم في اليوم الثاني للمؤتمر، وأتمنى أن تكونوا قد استمتعتم في اليوم الأول. Today we have a keynote speech, and then we have 3 other sessions. And I'm sure that you will enjoy each one of them, because they all will lead you to the future of the 21st century university. Our keynote speaker is Professor Dudley Herschbach. I feel very sorry to say that he is not here for a reason, but his mind is with us. His speech is with us. He had a car accident 2 weeks ago. He was very much interested in coming to attend and share with us his expertise. He and his wife, who is also a Harvard professor. But sometimes things happen beyond your wishes. So Professor Herschbach had earned his BS in math in 1954 and Master of Science in Chemistry at Stanford. And then he obtained his PhD in chemical physics in 1958 from Harvard too. He became a junior fellow at Harvard from 1957 to 1959. Became an assistant and associate professor at at University of California, Berkeley between 1959 and 1963. Well, it's a long CV, and I must read all of it because it is really important. He shared a Nobel Prize in 1986 with Jan Lee and John Polanyi. He taught graduate courses in quantum mechanics, molecular spectroscopy, and collision theory. And he gave many courses in chemics. He was an invited speaker all over the world. He's an emeritus at Harvard since 2003, but continued since then to teach freshman seminar on molecular motors, as well as in other universities. I will leave you with his speech that will be delivered on a videotape that he insisted in keeping his wishes, at least to talk to us and to give us the lecture that he thought of delivering while he was here. So please welcome me, Professor Herschbach, so that we tell him that you welcome him this morning. I just want to mention that we will...
My father had a favorite saying, "The difficult we do immediately, the impossible takes a little longer." The second phrase appealed to me as a kid, I suppose because of its heroic ring. That appeal has endured. Again and again, I've seen intrepid, persevering innovators achieve wonderful things regarded as impossible. This year's theme of the Ieche, the 21st Century University, foresees such an impossible achievement in higher education. In our digital age, higher education can be made accessible to the entire global population. The benefits to humanity could be immense. Many educators attending IECHE are already embarked on this awesome project. Rather than attempting to predict how that will unfold, my talk will focus on an inspirational story. It's about an impossible educational triumph achieved in a previous century. First, however, I tell a story of an impossible educational triumph. It conveys key aspects of the scientific enterprise, including the practical value of curiosity-driven research and the kinship of science and humanistic arts. The story involves Alexander Graham Bell, Helen Keller, and her teacher, Annie Sullivan. Many of you will have known much about Keller and Sullivan, but few may know how much Bell was involved. Bell patented the telephone in 1876 at the age of 29. Thereafter, he devoted many years to pursuit of other inventions, but he regarded his life's work as the education of the deaf. His mother and his wife were deaf. His father and grandfather, teachers of speech. His family had immigrated to Canada from Scotland after both his older brothers had died of tuberculosis. They settled near Toronto. Bell, in 1871, began teaching the deaf in Boston, and the next year founded his own school there. It was an effort to develop a device to help some of his not entirely deaf students distinguish between the sounds of the letters P and B that led to his invention of the telephone. Now, the technology needed to produce the telephone all existed by 1872, and several experts, then called electricians, were trying to invent it. Bell was not expert. In fact, he knew nothing about electricity and magnetism when he started work on what became the telephone. Yet after 18 months of intense effort, he became the successful inventor. Why? Why him? In later years, Bell liked to say that he would not have conceived the principle of the telephone if he had known more about electricity, but less about the mechanics of music and human speech. In fact, he was a good pianist, and it was while playing the piano at the home of his future wife that he had the key idea that made the telephone succeed. The piano soundboard works much like the diaphragm in the telephone. Helen, deaf and blind since an illness at 19 months, was at the age of 6 brought to Bell by her parents to ask his opinion whether she could be educated. Bell made arrangements that led to Annie Sullivan becoming Helen's teacher. Annie was then 20 years old, still suffering from effects of trachoma, which had made her temporarily blind for a few months. Because of her blindness, she was removed from the orphanage where she had lived and had no education to the Perkins School for Blind at Boston, where she had 2 years of education, only 2 years. But she graduated as a valedictorian, having written a superb speech. But Annie had no teaching experience, not much to guide her except her good sense and acute sensitivity. When she first worked with Helen, she had to deal with a wild creature. Helen had continual wild tantrums and frustration because of her handicaps. Yet only a month after Annie joined Helen came the great moment when Helen discovered things had names, when Annie held her hand in a stream of water while moving her fingers to give Helen the name. Within 3 months, Helen was writing brief letters. Within 3 years, she had an astounding command of idiomatic English. Helen's success was hailed as a miracle. Mark Twain, for example, thought so, and many others. But Bell had a different view. Especially in the early years and for decades later, he helped and supported Helen and Annie in many ways and knew just how they worked together. Bell insisted that Helen's mastery of idiomatic English was not a case of supernatural acquirement, but a question of instruction, a brilliant experiment by Annie. Bell concluded that the key was Annie's, and I'm quoting now, constant spelling of natural idiomatic English into Helen's hand without stopping to explain unfamiliar words and grammar, and her encouragement of Helen's reading book after book in Braille with a similar reliance on context to explain new language. Bell stressed that this was equivalent to the way a hearing and sighted child learns. Annie, in her own description of her teaching, confirms that she purposely never explained anything unless Helen asked a question. Thereby, Annie helped Helen to discover and actively exercise her ability to discern cues and context and to learn on her own. Here is a photo taken in the garden of Bell's Washington home. At this point, Helen was 16, Annie was 26 or 28, and Bell was 45. As you see, Annie is communicating with Helen as Helen reads her lips with her left hand, and with her right hand, Helen is communicating with Bell by fingers. It's a very beautiful scene. Now, science has a lot in common with this story. The teaching style of Annie Sullivan is intrinsic to frontier research in science. Nature is a reticent teacher. She speaks to us abundantly, but in many alien tongues. Alien, not foreign, alien. She does not offer explanations. It's up to us to ask probing questions and generate our own understanding. In frontier research, we try to discover or add to knowledge of the vocabulary and grammar of some strange dialect of nature's. To the extent we succeed, we gain the ability to decipher many messages that nature has left for us. No matter how much human effort and money we might devote to solve a practical problem in science or technology, failure is inevitable unless we can read the answers that nature is willing to give us. That's why basic, so-called curiosity-driven research is an essential and practical investment, and why its most important yield is ideas and understanding. We are all born deaf to much of nature's language, and it takes persistent groping and guessing to learn something of it. There are implications, clearly, for science education. In introductory courses, I urge students to approach the study of science like that of a foreign language. As you know, it's often said about language learning, once you get it in your ear, it gets easier and easier, otherwise harder and harder. Actual counts have shown that in introductory science textbooks for high school or college in chemistry, biology, physics, the number of new words or ordinary words used with special meanings exceeds the vocabulary of a typical one-year language course. Likewise, the array of interlocking concepts met in a science course functions much like grammatical rules. Now, the impossible empowerment of Helen by language exemplifies the highest aim of education, to install the habit of self-generated questioning and thinking, of actively scrutinizing evidence and puzzling out answers. We must try to encourage our students to strive to attain understanding rather than ritualistic training, cultural perspective and self-reliant thinking rather than conventional knowing. Such an approach is equally applicable to science and the humanities. For both novice scientists and students destined for other careers, teachers should emphasize the human adventures of intellectual exploration and help students take ownership of the subject. Take ownership. Now, what makes impossible possible so often in science? I think fundamentally it's because science enjoys a tremendous advantage over most other human activities. The goal, call it truth or understanding, waits patiently to be discovered. That's why marvelous advances can be achieved by ordinary human talent, given sustained effort and freedom in the pursuit. Far more formidable are enterprises such as business or politics, sports, sadly war. There the objectives may shift rapidly, so a brilliant move often becomes a fiasco rather than a triumph, because it comes a little too soon or too late. I like to also point out to students that to become a scientist is somewhat like becoming a musician. Even if you have talent, you must work hard to master your instrument and the literature and the culture that you will serve. But the scientist can and surely will play many, even most, of the notes wrong. When he or she gets one right, they will be appropriately applauded for doing so. The patience of scientific truth has another important consequence. Often what might appear as the most promising approach does not pan out. There are unanticipated roadblocks. Then it's vital to have some maverick willing to explore unorthodox paths, perhaps straying far from the anticipated or consensus route. In science, it's not even desirable, much less necessary, to be right at each step. At the frontier, scientists are heading in wrong directions much of the time, optimistically looking for new perspectives. I like a quote by Richard Feynman. He said, "Science is not about what we know, it's about what we don't know." Now, the consequences for education are obvious and ironic. Science as met in typical high school or college introductory courses is sadly at odds with the adventurous, exploratory character of research. Such courses too often come across as a frozen body of dogma. The questions and answers seem to have only one right answer to be found by some correct procedure. The student who does not easily grasp the right way or finds it uncongenial is likely to become alienated. There seems to be little scope for a personal, innovative experience. I point out to students that doctors don't expect patients to appear and tell them just exactly what they need to know, nothing more, nothing less, which is a standard thing in the problems and test questions the students face. That's far from what actual frontier science is like. At the outset, nobody knows the right answer, often not even the right question or approach. So the focus is on asking an interesting question or casting the familiar in a new light. Where do you encounter that approach? It's in artistic creations. There, the focus is not about getting a right answer, but offering a fresh view of something that stirs thoughts or emotions in the observer. Likewise, scientific work seeks to open up perspectives that stir other people to further explorations. Like art, science is a social enterprise. Its progress depends on the response excited in observers. A good way to combat inhibitions induced in students by too much focus on right answers is to have them write poems with science themes to enjoy personal freedom and make some topic their own. Here's an example from a freshman student. She titled it Quantum Land. Do you know a special secret place filling much of invisible space where frogs can only jump so far and the range of an ordinary car can be only 10 or 20 miles? And every person has only half or whole smiles, where dogs bark at specific levels of pitch and people can only be a certain amount rich. I have hundreds of poems like that from the students, and they love to do them. I also award prizes for the poems. There's a book by a science outstanding spectroscopist of the early decades of the 20th century, Robert Williams Wood. He made wood cuts in linoleum of poems he wrote, and he titled the book, How to Tell the Birds from the Flowers. He would, for example, draw a parrot and a carrot to look amazingly alike. And then he'd have a little poem to tell you about distinctive, important differences and similarities. The kind of thing that you need to be alert to in both science research and science education. His poem goes, the parrot and the carrot one may easily confound. They're very much alike in looks and similar in sound. We recognize the parrot by its clear articulation, for carrots are unable to engage in conversation. I like to show students poems by poets that weren't intended, but do, in fact, pertain to science. There's a Czech poet, Jan Sekel, who wrote a short poem saying, poets don't invent poems. The poem is somewhere behind. It's been there a long, long time. The poet merely discovers it. That harkens back to what I pointed out about the patience of scientific truth. Clearly, guessing is intrinsic to science. It's naturally done a lot in learning language. It's a powerful aid as seen with Helen Keller. But the usual way of teaching science makes students reluctant to guess. It should be fun. It can be fostered by class discussions in which groups of 3 or 4 students consult with each other to formulate and defend a guess. Many of you here must have heard Eric Mazur describing what is termed now peer instruction in his class. And you probably saw his movies that show the excitement of the students in proceeding that way. I like also to tell my students that not so many years from now, most of you will be considered expert in something. Then you will find that clients often come to ask your opinion, not because of what you know, but because they think as an expert you can guess better than they can. I want to finish with a Nobel benediction. You've probably seen the front face of the Nobel medal many times, but the reverse face of the medal deserves attention. It intends to convey the significance of the awards. Here I show you that reverse face for the physics or chemistry medal. It depicts, if you can make out the little Latin inscription, Scienta gazing upon the face of her teacher, Natura. These two elegant women, perched among billowing clouds, have Natura standing tall, holding in her right hand a cornucopia, conveying what riches await us if we pursue the study of nature. The kneeling figure, Scienta, wears a laurel crown and has in her left hand a scroll representing what we have achieved in the way of hard-won knowledge. Scienta reaches up with her right hand to unveil the face of Natura, which she beholds intently. The unveiling motif, familiar in classical antiquity, aptly represents the aim of scientific research. It pertains just as well to scientific education. For me, this reaches beyond metaphor. These earnest and lovely figures readily morph into another immortal pair, teacher and student, Annie Sullivan and Helen